Hello, I'm Ostenaita from the University of Helsinki, and I'll be talking about noise-aware statistical inference with differentially private synthetic data. I'll start by giving a short introduction to our work and go into technical details later. So, synthetic data offers a compromise between data availability and privacy by using a real data set to train a generative model and then sampling synthetic data from that model, which can then be made available for analysis. And ideally, the synthetic data would preserve the population level quantities of the real data, so the analysis should be useful. But the synthetic data doesn't contain any records from real people, so it should preserve privacy. And the privacy preservation can even be quantified by using differential privacy, which is what our work does. Now, a natural question is, can we just analyze the synthetic data like real data? It turns out that in some cases we can't. For example, if we want uncertainty estimates, like confidence intervals, they become overconfident if you ignore the synthetic data generation in your analysis. In like the plots here, we have a very simple example which demonstrates this. First, we generate the real data from logistic regression with two coefficients, which correspond to the two panels here. Then we generate the synthetic data with one of these four differentially private data generation algorithms. And from the synthetic data, we infer the coefficients of the logistic regression, like we would infer them with real data. And on the y-axis, we have the coverage, which measures how often the confidence intervals contain the true parameter values. And we are computing 95% intervals, so the coverage should be 95%, which is where the black line is. And on the x-axis, we have epsilon, which measures the differential privacy guarantee. 0.1 is a very strong guarantee in terms of privacy, and then 100 is almost meaningless. And you can see that no matter what the algorithm to generate synthetic data or the privacy strength is, the coverage is not at the promised level of 95%. So the confidence intervals are overconfident. All right, our solution to this problem is called noise-aware multiple imputation, or NA plus MI. Multiple imputation was originally developed to deal with this problem of uncertainty estimation, where when imputing values when you have missing data. And it was later adapted to deal with synthetic data. The idea there is that you generate multiple synthetic data sets, analyze all of them like you would analyze the real data, and then combine the results with so-called Rubin's rules, which then allow you to compute, for example, confidence intervals. And generating the multiple synthetic data sets and then getting the multiple analysis results is important because they allow the combining rules to account for the extra uncertainty from generating synthetic data. And originally, this was developed in a non-differentially private setting, but it turns out that we can use this with differential privacy if the algorithm we generate synthetic data with is noise aware in a certain sense, which I'll get into in the more technical part. Here are the results from the previous example. In blue, the results are for our algorithm, which is very close to the promised guarantee. We also have this other algorithm called PrevelCM, which is theoretically compatible with our framework, and which is what we use with these results. But in practice, it gives either overconfident results in some cases, or in most cases, it gives underconfident results. So its intervals are too wide. So to conclude this short summary, estimating uncertainties from synthetic data requires accounting for the synthetic data generation process and also differential privacy if that is used. And our framework, NA plus MI, allows for accounting this extra uncertainty under differential privacy when you have a noise-aware synthetic data generation algorithm. And next, I'll go into the technical details on a high level and some additional results. All right, first I'll give some background on differential privacy. So the reason we want to use this is that very accurate synthetic data can still allow adversaries to compromise the privacy of the data subjects. But differential privacy is a property of an algorithm that quantifies the privacy loss that results from publishing the results of the algorithm. And this quantification is done by limiting how much the probabilities of different outputs can change when you change just one row of the input dataset, which is done by through this inequality you see here, which depends on the numbers epsilon and delta to quantify the privacy guarantee. One very useful property of differential privacy is post-processing immunity, which means that any post-processing on the output of the algorithm cannot reduce the privacy bounds. And as we've seen, this definition can be applied to generating synthetic data. And currently there are many algorithms that can do this. But all of these algorithms that use differential privacy require adding extra noise, which makes this uncertainty estimation problem even worse, because when you're just using the real data process, you're just going to ignore the extra noise. So next, I'll give some extra details on NA plus MI. So even in the non-DP case, the synthetic datasets need to be generated from a posterior predictive distribution so that the combining rules can accurately account for the uncertainty. And when we are using differential privacy, this posterior has to take the differentially private noise into account. So in the posterior predictive here, we're using the S tilde, which is a noisy summary of the data instead of the real data set. And this is what we mean by the noise awareness of the data generation. All right, so we need to develop some kind of algorithm to actually do the noise aware generation to implement our framework. There is some work on noise aware Bayesian inference, for example, by Bernstein and Sheldon, but their work only applies to simple exponential family models, which doesn't get us very far with realistic datasets. So we want to generalize their framework to more complex models. And the general idea of our algorithm is to focus on discrete data, which is summarized by marginal queries. Then add Gaussian noise to the query values to get a DP guarantee. And then infer the posterior of the Bayesian model, which includes this Gaussian noise, which is what makes this algorithm noise aware. And then finally, we sample the posterior predictive to generate the synthetic data. And we're calling this algorithm noise-aware private synthetic data using marginal queries, or shortened to NAPSU-MQ. And because of post-processing immunity, we can generate an arbitrary number of synthetic data sets without affecting the privacy bounds. And we could even release the posterior from step 3, which allows the analysts to generate synthetic data if they need to. All right, so next I'll give a quick example of marginal queries. So the marginal queries simply count the number of rows with given values for given variables. So for example, we could have a marginal which checks if age is between 30 and 39 and income is not over $50,000. And for this example data on the right, the result would be 2. And a single marginal query doesn't get us very far. So we actually want to look at full sets of marginal queries, which contains all of the marginals for given variables. So for example, for age and income, we have 2 values for age and 2 values for income. So we have 4 marginal queries in the full set. And we can also have more than 2 variables or just 1 variable in the marginal query, in which case it is called a k-way marginal when there's k variables. Next, I'll go over the Bayesian model, starting with the variables on the right. First, we have theta, which is the model parameters that generate the real data, which is x. Then we have the marginal query values S and the noisy marginal query values S tilde from the Gaussian mechanism. We also have X star, which represents a hypothetical data set, which is used in the posterior predictive distribution. We model the distribution of X given theta through 3 constraints. First, we require that the marginal queries have the correct expected values. Then we require that each individual data point in X is IID. And we also require that the distribution has maximal entropy. These constraints give the following distribution over here, which we give for a single data point in X. And we call this distribution the maximal entropy distribution, or just MED for short. Now we get this Bayesian model at the top. Unfortunately, we can't just sample the posterior because S is a fairly complicated discrete variable. So to get rid of S, we first do a normal approximation on it. And then we marginalize doubt now that we have the 2 Gaussian distributions there. And now this is a distribution which we can sample with standard posterior sampling methods. Of course, we need to compute the mean and covariance of the normal approximation, which are mu and sigma. But we can do this with techniques from probabilistic graphical models. Next, I'll go into some results, starting with the adult dataset. At the top here, we again have the coverage on the y-axis, which is how often the confidence intervals from synthetic data contained the true parameter values, or in this case, the parameter values from logistic regression with the real data set. And on the x-axis, we have the confidence level. And because the confidence level promises that the coverage is at least the confidence level, we would want to be as close to the diagonal as possible, which is roughly where our algorithm is. And at the bottom, we have the ratio of the synthetic data confidence interval width to the real data confidence interval width. And here you can see that the overconfident algorithms generate intervals which have the same width as you would get with the real data set. We also have another algorithm called PGM repeat here, which simply splits the privacy budget into m parts and then repeats PGM m times to get m synthetic datasets, which you can use with NA plus MI. It doesn't exactly meet the assumptions for the combining rules, so it actually turns out that it's underconfident, which you can see here. Then we also have similar results for the US Census dataset, which is a much larger dataset, which is probably why PGM is actually performing fairly well with the larger epsilons. Our methods also have some limitations. NUPSO-MQ is limited to just marginal queries on discrete data, but this is not that severe because continuous data can be discretized. A more severe limitation is that the selected queries must contain the relevant information for the downstream analysis, which means that the synthetic data generator has to either know a lot about the downstream analysis, or they have to include a lot of queries, which will make the Bayesian inference tasks very expensive in computation. And it is already very expensive, even with a fairly small number of queries, which we use in our experiments. So to conclude, estimating uncertainties from synthetic data requires accounting for extra noise. And our methods NA plus MI and NUPSO-MQ allow doing this under differential privacy. And our experiments show that this gives accurate uncertainty estimates. We have an implementation of our algorithm available in the Twinify library, which also contains some other tools for DP synthetic data generation. All right, that is all. Thank you for listening.